In this session, we will derive an expression for the mutual inductance of two coaxial circular coils. Now, first you take down a question, and based on the question, we will derive the equation. Two concentric circular coils, C1 and C2, comma radius R1 and R2, and in bracket you can write R1 as very less than R2, or R1 is very less when compared to R2, respectively are kept coaxially. If current is passed through C2, then find an expression for mutual inductance between the two coils. Okay, so let me read once again. Two concentric circular coils C1 and C2, radius R1 and R2 respectively are kept coaxially. If current is passed through C2, then find an expression for mutual inductance between the two coils. Now first we will try to draw a figure based on the given situation. Now what is given? These are two coils. There are two coils C1 and C2 with different radii, and they are placed coaxially. What does it mean? Coaxis means common axis. So we can say that it is a concentric circular coil, so they will have, both of the coils will have same center, and the radii are given. So now let us draw two coils with the same center. So let me say here is the center. Now the second coil will also have its center here, but its radius will be very less compared to the first one. So now we'll draw another coil, something like this. Okay, so this is, we'll mark these coils. One is C2, the other one is C1, and C2 has a radius of R2. Radius is R2, and the radius of C1 is R1. Now the current is passed through C2, so we can assume some current, say I2 is passed through C2. I'll take the suffix I2 itself because to say C2, R2, etc. So for simplicity I can take I2, or you can take I1 also, no problem, but it is in the second coil, so I will assume the current as I2, and you can assume any one direction. I will assume anti-clockwise direction. So this is the given situation. So given situation we have shown using this figure. Now what we have to find out? We have to find out mutual inductance. Now how does this term comes into picture here? We have a current in one coil, and the current in one coil produces magnetic field or magnetic flux, and the flux also links another coil which is placed coaxially with the coil through which the current is passed. So therefore a mutual flux. The flux produced by the second coil also links the first coil. So as per the definition, the mutual inductance here is given by phi 2 by phi1 by I2, or first we'll write all these quantities like what is R1, what is R2, what is I2, etc., and then we will try to find out what is the mutual inductance. So C1, C2, everything we have written, no need to write it once again. So let I2 is the current through C2. So B2, let us say B2 is the field, let B2 is the magnetic field at the center due to current I2. Why I am finding magnetic field at the center is the question. Now here, see, the given condition is R1 is very less than R2. The radius of R1, the radius R1 is very less compared to R2. So you can consider the coil C1 is almost at the center. That is why you find out what is the magnetic field at the center due to current I2. And you know how to find out the magnetic field due to a circular loop. Let phi1 is the total flux linking coil C1. Total flux linking coil C1. Now mutual inductance M is given by flux linking the first coil due to current in the second coil. So it is M is phi1 by I2. Now we need to find out what is phi1. So the flux linking the first coil will be equal to magnetic field at the center, that is B2 into A2 or A1, because it is the first coil, right? So B2 into A1 into number of turns in the first coil, where N1 is the number of turns in the first coil. If N1 is equal to 1, then this will become B2A1. So we will do in general case where we will take, the coils have a number of turns of N1 and N2. N1 is the number of turns in coil C1. N1 is the number of turns of coil C1. A1 is the area of cross section, okay, that you know, no need to write it. A1 is the area of cross section of coil C1. Now what is B2? B2 is the magnetic field at the center. So B2 is given by, if you have a circular current carrying loop and with radius R, the magnetic field at the center BC or magnetic field at the center is given by mu naught into I divided by 2R. If you have a circular loop and if it carries a current I and the radius of the loop is R, the magnetic field at the center is given by mu naught I by 2R, and if it has n number of turns, then you have to multiply this equation by n. So apply this same formula for this case where current is through C2. So B2 is mu naught into what is the current? I2 divided by 2 R2, and let us say the coil C2 has N2 number of turns. Magnetic field at the center multiplied by N2. So N2 is the total number of turns in coil 2. Okay, so now phi 1 as B2, that is mu naught I2 into N2 divided by 2R2, mu naught I2 N2 by 2R2 into A1. A1 can be written as pi R1 square, because R1 is the radius of the first coil, into N1. So substitute the value of B2 in the equation phi 1. Now mutual inductance. M as phi 1 divided by I2, it's because the current in the second coil, phi 1 by I2. Now this will be equal to, substitute phi 1, that is mu naught into I2 into N2 N1 into pi R1 square divided by I2. Okay, now cancel this I2. What do you get? M is equal to mu naught into pi R1 square into N1 N2, and I think I left one quantity here, that is 2R2. Because we have in the denominator 2R2, this will be divided by 2R2. So this is the required expression. The mutual inductance M is mu naught pi R1 square into N1 N2 by 2R2. Pi R1 square is actually A1. The mutual inductance M is given by mu naught into pi R1 square into N1 N2 divided by 2R2, and this is the required expression. This is the required expression, and hope you understood this derivation.